In this segment, we're going to talk about why certain things are true from the previous segment. So namely, we're going to answer the question, why does every basis have to necessarily have the same number of vectors? And we're going to answer the question, why is it the case that any n linearly independent vectors in Rn form a basis? So let's just jump to the first question. And to do this, we're going to need two important facts. So the first fact is if we have three vectors which are the result of multiplying by A. So in this case, these are the outputs, AW1, AW2, AW3. If those are linearly independent, then so are the before vectors. And the second thing we're going to need is that if you have more than n vectors, so more than n vectors in Rn, they must be linearly dependent. So we're going to use these two facts together to prove that every basis of any vector space, at least finite dimensional vector space, has to have the same number of vectors. All right, so how is this going to work? So one thing we're going to do is we're going to make an assumption. All right, so what we're going to do is we're going to live in a fantasy world. We're going to assume, right? We're going to assume that a vector space has a basis, say, with n vectors, and another with n minus 1 vectors. So we're going to assume this. And what's going to happen is we're just going to keep going until we reach some bogus contradiction and we kind of wake up from this dream. Right? We assume this assumption that we're living in this fantasy world is false. We're going to wake up from this dream. So that means that this assumption is going to be false. All right, so we're going to call these vectors, we're going to call these n vectors. We're just going to call them E1 through En. And we're going to call these n vectors, we're going to call them V1 through Vn minus 1. Okay, so one key thing to keep in mind is that a basis means that you can write every vector in that vector space as a combination of them. So in particular, if V1 through Vn minus 1 form a basis, which they do, we can write E1, just think of this as any old vector, I don't care what it is, we can write that as some combination A1 times V1 plus A2 times V2 all the way to An minus 1 times Vn minus 1. It's some combination of those. And we can write E2 as some other combination of those same vectors. And this keeps going. Oh, that should be a B. All right, so one important thing to keep in mind is that this may seem very abstract, but I want to point out that this form, we can write all of these as a vector matrix. So the V's are vectors, but the A, B's, and Z's are just scalars. So we can write this, another way of writing this is in fact, for example, E1 is really a matrix comprised of all of these vectors times some vector A1 to An. right? And likewise, E2 is going to be the same matrix times a different vector. And all of the E's are some matrix times some vector. All right, so now what's going to happen is, keep in mind, if you're a basis, you also have to be linearly independent. So a basis is linearly independent. Which means all of these have to be linearly independent because they formed a basis. So altogether, we have that all the EIs, all those E vectors that we had before, are equal to some matrix A. This A is just this concatenation or amalgamation of the V vectors times some, some other vector. Okay, let's call it WIs. And the WI is just this vector over here. This is just W2, and this is just W1. There's just some W vector that does this. So all the EIs looked like this. All right, so now we're going to apply the first fact. So the first fact says that if you have this, and this works for any number of vectors, not just 3, though 3 is convenient. If you apply this fact, since all the EIs are outputs of them, and they're linearly independent, this implies by the first fact that the WIs are linearly independent. All right, now we're gonna have this big but. So that we used fact 1. This is fact 1 right here. You applied fact 1 that since the EIs are an output, you get this. We can conclude that all these W's are here on the right are going to be linearly independent. All right, but now here's our big but. But those WIs, what space do those live in? Those W's all are in, these are in our, they're in our n minus 1. So the WIs live in our n minus 1, but there are n of the W vectors. So keep in mind, every E had a W vector. Every E we wrote as this big matrix A times some vector, and we did this for all n of them. So there's n W vectors. There's n W vectors, and they live in Rn minus 1. So by the second fact, they must be dependent. You have too many vectors to be independent. All right, so now we have a contradiction, right? The WIs must be dependent, but on the other hand, the WIs must be independent, and that's not possible. So we can wake up from our dream, and our assumption, the main assumption we made from the dream, was that there were two bases for the same vector space that had different numbers of vectors. So this assumption is bogus because it makes us wake up from our dream. We get two contradictory things. So this assumption is false. It cannot be the case that you have different numbers of vectors in the vector space. So this may seem like a lot of abstract noise, but I would encourage you to kind of go through this and make sure you understand it. And in particular, that you especially understand exactly what these two key facts are saying, and that these two key facts make sense to you. This first fact is especially important because this was actually a homework problem assigned previously. So that's why every basis has to have the same number of vectors. All right, so let's jump to number 2. The second question was, why is it the case that every collection of n independent vectors in Rn, those form a basis. So this is kind of the key point to get across. Right, so one thing to keep in mind is basis requires two conditions. One is they have to span. You have to have enough vectors to span your vector space. In this case, they have to span Rn. But two, they have to be linearly independent. So what I'm saying is, if you have n linearly independent vectors in Rn, okay, you meet the second condition. But what I'm saying with the key point is you're guaranteed the first condition. But it may not be clear why that's the case. Okay, so let's go through why that's the case. Let's just kind of go through one concept at a time. So one thing that we've had is that if you have n independent vectors, they have to pass the independence test. Namely, that you can take this matrix right here, you can take all those vectors, if you concatenate them, amalgamate them into a matrix, that they're going to reduce to the identity matrix. All right, that's the independence test. If you can reduce them to the, not necessarily the identity, but more importantly, they have a pivot in every row, right? If they have a pivot in every row, then, or sorry, every column, if they have a pivot in every column, they're going to pass. Now, the only way to do that with n vectors is if you happen to get exactly the identity matrix. There's no extra room to miss any, to kind of have more to skip a row in some sense. You can't skip any rows. All right, so what does this mean? Well, if you reduce the identity, this means that this matrix right here, this amalgamated matrix of vectors, is invertible. You can find the inverse. Well, if it's invertible, what does this mean? That means if we consider the equation AX equals B, where I'm taking A, this A right here is just this matrix. So this equation AX equals B has a solution, and it has a unique solution for every B. So for every B that you pick, it has a unique solution for X. So you pick a B, I can find a unique X, and namely, what is that X? That X is going to be A inverse B. All right, so what does this mean? This means that every B you can pick in Rn is equal to some matrix inverse, but some matrix times the vector X. And so this means if we write down this X as, sorry, no, it's every, no, just like that. Every B, not inverse. Every B is the matrix times X. If we write down this X as just a bunch of single numbers, we get this matrix. And this matrix multiplication is really equal to Vx, right? Vector matrix multiplication is the same thing as just taking this column times the corresponding entry. So this is just x1 times v1 plus the next column times the next entry. So this is a little backwards from RC Cola, but one way of thinking of vector matrix multiplication is it's a linear combination of the columns of the matrix. All right, so what this says is every vector in Rn, every B, is represented as some linear combination of our VIs, and this implies that every B in Rn is in the span of our V1 to Vn. So now we're in the span. So what does all this mean? This means that if we started all the way up here, if you have n independent vectors, V1 through Vn, they give them to me, and those live in Rn, right? Those have to pass the independence test, which means that the corresponding matrix is invertible, which means that there's a unique solution, which means that you can write every vector B as a linear combination of those original Vi through Vn, which means that every B in Rn is in the span of this, and that's exactly what we were missing up here. So that tells us that any n independent vectors in Rn themselves form a basis. And that's why this is true. One of the other key takeaways is hidden in this is actually right here, is that this also gives you another independence test or invertibility test. So for example, if you have n independent vectors in Rn, right, kind of the first thing we kind of did was make this matrix and conclude that it has to be invertible. So you know a matrix is invertible if it's square and if its columns are independent, and vice versa. You can also check if vectors are independent by seeing if there's an inverse, though you probably wouldn't use this fact that way. It does work this way. And these are all equivalent notions of the same thing. These are all related. Independent vectors in Rn, if you have n of them, that forms an invertible matrix. That implies there's unique solutions for every possible B, and that implies that they form a basis.